Hello everyone, this is Diptosri, the coordinator of PICS Today webinar series. I cordially welcome you all on behalf of COEC PICS IIT Madras. I would like to extend my heartiest welcome to Professor Christine Silverhorn. She is the chair of Integrated Quantum Optics Group in Paderborn University. Professor Christine will give a talk on quantum photonics. Before having this most demanding talk, I would like to request Professor Bijay Krishna Das to introduce our honorable speaker. I'll also request Professor Deepa Venkatesh to moderate our Q&A session. Over to Professor Das.
Yeah, thank you, Diptasri, and I also welcome everyone. And it is my pleasure to introduce Christine Silverhorn, Professor Christine. Of course, she is a German physicist, specialization in quantum photonics, and currently heading Integrated Quantum Photonics Group, Quantum Optics Group, I would say, at University of Paderborn. I think just bearing the legacy of Professor Scholer's lab, lithium niobate integrated optics, which was formerly known as ungoverned physics. So from where I also got my PhD degree. And yeah, Silverhorn is best known for her role in leading research projects which develop mostly quantum devices and systems for quantum computation and quantum communication. So in 2005, Silverhorn joined the Erlangen branch of Max Planck Institute for Quantum Optics, GERSI, heading the junior research group, namely Integrated Quantum Optics again until 2008, where she completed her habilitation. I think that is a very honorary degree to enter. If you want to be a faculty professor in German universities, you have to complete that habilitation degree. So she had it in 2005. And then in 2008 onwards, she was leading the Max Planck Institute for the Science of Light in London, that was established that time. And then until 2010, she continued there, I think. Then afterwards, she joined in Paderborn University, I think, yeah. So her research work has been awarded by several prizes. I think prestigious prizes like Gottfried Wilhelm Leibniz Prize in 2011. And 2017, her team was awarded with the prestigious European Research Council Award, Consolidator Project Grant for quantum photonics research. She is also elected member of the Leopoldina, which is also prestigious in North Rhine-Westphalian Academy of Sciences, Humanities and Arts. And also she is a fellow of the Optical Society of America. So she became a fellow for the Max Planck School of Photonics in 2019. And yeah, her work in this area really actually you can just imagine for. And with this short introduction, I invite Professor Christine just to take over. And also in the panel, we have Professor Thagarajan, who is also our mentor, from whom we learned photonics, and also well known to Christine. I think you can put up all your Q&A in the chat box as instructed. And Deepa is the moderator, and maybe 40 to 45 minutes after her talk, we will have a very useful interacting Q&A sessions. And also our CTO Arnav Goswami is there. She can also participate in the panel discussion. With this, I just welcome Professor Christine. Please, over to you. Yeah.
Well, let me first try to start my presentation. 1 minute. Should work. We tested it. Okay. I hope you can see it now.
Yes, it is fine.
Okay. So let me start with thanking you very much for the nice introduction and also for that invitation and giving me the opportunity to present my work here. Now, the presentation I entitled Quantum Photonic Using Nonlinear Integrated Optics and Pulsed Light. And it's a pleasure to present you that work. And it's basically an overview what we're doing in my group. Before starting to really going into details into these topics, I would like to give you a physical motivation about the things we are doing. And one of the core ideas is we want to build quantum networks. Why quantum networks? Well, quantum networks I consider as an ideal model system for having a complex large-scale structure. And quantum networks, of course, one thing which you probably immediately have in mind is the quantum internet. And of course, this is also an important topic. But it's going beyond that. If you want to understand transport phenomena or neural networks, you see all of these network structures in there. And the question is, what does these networks make quantum? Now, this is actually not a question which is very easy to answer, but I hope by the end of the talk, you will understand more what I mean by that. Secondly, I'm a photonics person, as you have also heard already. And if you're coming from photonics, what we are trying to do these days is to establish multi-dimensional photonic quantum systems, an ideal really very multi-dimensional, that means large-scale quantum systems. Why is that? Well, one of the motivation is to have photonic quantum computation and simulation. I will come back to that in a minute. And we had a breakthrough experiments there from China in 2020. But multidimensionality also plays a role in our quantum technologies like quantum metrology, where we're looking at multi-parameter estimation. And last but not least, we are talking about photonics. We are talking about light as information carrier. And of course, quantum communication is also an important topic. And it's interesting to note that also there, high dimensional information encoding is an important topic, which I also will address. Let me say a few words about photonic quantum computation. Photonic quantum computation, where people started to look more seriously into that, I think was around 2001, where Nilda from Melbourne suggested their LOQC. This was a very important milestone from the theoretical side, but it was also clear that the overhead we need to implement such systems is huge. This is nowadays phrased different or elaborate on measurement-based quantum photonics, and we still want to do these things to establish universal quantum computation. At the same time, we are trying to figure out systems which are easier to implement and have a more near-term future. And this brings me to the topic of quantum simulation. And here I will show you some of our works in quantum walks, which are targeting towards quantum simulations and understanding the foundations of that. Last but not least, in that context, I want to mention boson sampling. Boson sampling is quite interesting from a photonics community because it's a rather simple system. And here you see what kind of system it is. You have a unitary matrix, that means a linear network. You input n single photon states in the original proposal, and you just detect at which output ports the photons come out. Surprisingly, these rather simple looking experiments can't be calculated computationally. So you can, by demonstrating this system, you can demonstrate quantum computational advantage. And this was the experiment which I was referring to for quantum computation, which came from China in Shanwei Pang's and Shouyang Lu's group. It was a milestone for photonic quantum simulation because actually a system was implemented which can't be calculated classically. This was quite exciting. And it was particularly also exciting for us, I have to say, because if you look what kind of scheme they really used, it was not the original classical boson sampling experiment, but something which we nowadays call Gaussian boson sampling. And there, instead of single photon states as the input states, they used input squeeze states. And why did they do that? It is because it's easier to scale the system in the terms of photon numbers by using these squeeze states, which are easier to produce and can have high brightness. We were looking at that topic for quite some time together with Igor Yek's group. In 2017, we have suggested that instead of using the standard approach from boson sampling, where people are always looking at single photon input states, that you can use such Gaussian single mode squeeze states as input states. They have a very good scaling experimentally. So scaling means that you need fewer resources to implement that. And you still implement in this system a system which is equally hard to do classical or to simulate it classically. So here you measure Hafnians. And for us, it was very exciting to see that this works. And you can also say that you have to come up with clever ideas to scale up your systems. And this is actually a topic which we follow in my group in different ways. Now, let me introduce briefly the team. The Integrated Quantum Optics team is a team which has different aspects, different subgroups. First of all, you heard already, Paderborn has been known for quite some time for integrated photonics. And we have this integrated photonics on-site fabrication facilities, and I have a subgroup led by Christoph Eigner, where we produce all kinds of photonic devices in our own facilities. Then we bring these structures to the optics labs, and we build devices from that. The group leader here is Harald Hermann. And there we really build up optical circuits, we model things, and we really show quantum devices. And you will see something for that too. Last but not least, we also have the Quantum Networks group headed by Benjamin Brecht. And here we take the opposite view. We kind of look what kind of theoretical proposals are out there and what can you be implementing there. And there are quantum walks, which is related to the quantum simulations, and ultra-fast pulsed quantum optics is an important topic. And you see that this all is in a circle, and this is not a coincidence, because you also see the philosophy we're pursuing. At the end of the day, if you really want to implement these quantum technology applications, they really rely heavily that you have a good technology which is tailored to that needs, and you can have all these different aspects in one place. And this is what we're trying to do in Paderborn. Now, I told you that one of the challenges I see is to have good strategy for scaling these photonic systems. And in my talk, I want to give you a glimpse in all of these different topics, how you can scale photonic systems. The first one is integrated optics, integrated quantum optics, and there I want to show you our work in that area. Secondly, I will talk about time multiplex quantum systems because these systems really scale very nicely in terms of experimental overhead. And last but not least, I also want to talk about temporal modes of pulsed light. You might not see at the moment why this is scaling. It's coming from fundamental science and how to combine ultra-fast physics with quantum physics, but it's also a new way how we can try to make our systems larger in terms of having more dimensions we can encode information onto. Let me get started with nonlinear integrated quantum optics and our work in this area. Now, let me start because Paderborn also has a long tradition in integrated optics. And I should say, when I came to Paderborn, there was a very strong group, Professor Solar's group already there. And we were kind of had to learn from each other. And what I learned as a quantum optics person, so I'm really coming from the background of quantum optics, there is a lot of things which I have to learn from integrated optics. And actually not only learn, we really build a lot on these expertise which is there, and it's a good thing. So I want to start with an integrated optics introduction. It's actually from 1969, so you see it's an old overview article. The interesting thing is that this old article you can make very quickly in a very modern review if you want. You just add between integrated optics the word quantum. You sometimes replace the word laser beam circuitry by quantum beam circuitry. Some places you have to replace lasers by photons. Well, I don't want to go into detail, but this is hard. But anyhow, if you do that, then you can come to a conclusion, and already in 1969, people had the same vision. If realized, this new art would facilitate isolating quantum circuit assembly from thermal, mechanical, and acoustic ambient changes through small oval sites. Economy should ultimately result. And I think this should be very modern for you in terms of technologies. What are we doing these days? What is new? Well, we keep all the good ideas which is behind the scenes of integrated optics, but we adapt them to quantum optics. Well, this adaptation is not really easy because you have to tailor your system. There's a lot of technological work which has to go into that. And I have to say, over the last 10 to 15 years, we have been doing that, and this is good fun to do that. But it's also work which you have to do if you really want to succeed. Now, this is another review I'm presenting here about photonic quantum simulators from Alan Aspogusic and Philip Walter from 2012. So this is the vision, how you can imagine an integrated optics photonic quantum simulator would look like. So it's a hybrid integrated network where you have a source bit, a circuit bit, and a detection bit. Now, if you go look a bit closer, the circuitry is linear optics, so couplers typically, while sources always you need, if you have quantum source, some nonlinear action. And if you build a system like that, the advantage is that you have many spatial modes available, so the scalability is there, which can be rather simply controlled. You get the interferometric stability of large optical systems, which is important if you want to scale systems up. You have compact devices, you can miniaturize your devices, easy operation. Well, if it's operating as you want, you have to develop it, but it can be easily operated. And one of the challenges is that we need high efficiencies for that. Now, in the linear part, integrated photonics has really become a very hot topic. I think it's fair to say that it started in Bristol around 2008, and now I just cite European papers, but I think there's all over the world. Other work have been done in Rome, also in Oxford, and nowadays I think integrated photonics has become a whole field. Most of the work is still doing really the linear optics bit. And the thing which we have been focusing over the years was nonlinear integrated optics. And in particular, what we are looking for is to look for a material platform where this nonlinear integrated optics can be harnessed in the best way, which is the lithium niobate platform. The system we are looking at, we build our system still on rather established technology because we have extremely low waveguides that they have minimized the coherence, and for all quantum optics experiments, it's essential. We get the stability and the scalability. In contrast to many other platforms, our platform has a Chi2 nonlinearity, so we have highly efficient photon pair generation. And equally important, you have fast photon routing, and this is what's becoming a hot topic nowadays, because this fast photon routing is needed, and lithium niobate is an established material system to accomplish modulated systems. And what we are trying to pioneer is the implementing of complex quantum circuits on this platform. Now, for the source bit, we are typically using parametric down conversion sources where we have a waveguide in a periodically poled structure. We pump this waveguide by pump light, and due to the nonlinear action, a pair of photon signal and either photon pairs are generated. In order for this process to happen, we have to have energy and momentum conservation, such that the frequencies of the signal and idler photons have to add up to the frequency of the pump. The same has to be true for the propagation constants, and there the periodic polling is important. This allows us to have this momentum phase matching. In other words, well, the momentum conservation, in other words, the quasi-phase matching. I'm not going to detail, but we have, therefore, we can kind of customize our systems there. Having waveguide allows us to have a strong confinement of all optical waves. So we can have long interaction life and very efficient processes. And the samples we're looking at can be as long as 90 millimeter in our case. Now, you can ask what kind of different elements can you build on that platform? And this is kind of trying to categorize them. We have on this platform can have passive routing, like in all integrated optics. Lithium niobate has been used for photon pair generation, where we also did a lot of work on that. Up and down conversion for transducing between different wavelengths. Also, quantum memories have been demonstrated on this platform. Very importantly, you can have active manipulation with electro-optic switches. And last but not least, one thing which people quite frequently don't talk about, but you need also interfacing. So either fiber waveguide coupling or dielectric coatings, for example, to build up resonators in these systems. Now, all these things have been developed, and most of them for classical optical applications, but the thing we need to do is we have to tailor them now for quantum applications, so redesign optimizations. For example, in quantum optics experiments, quite frequently we want to have very short waveguides. This is simply because the coherence is so important that we have to reduce the losses. And this was when I arrived in Paderborn, people were quite surprised that I didn't want to have the long waveguides where we get a more nonlinearity, but a short waveguide, because this is quite frequently beneficial for quantum experiments. Now, I can't go into detail about all our devices, but I would just give you a kind of an overview. What kind of things did we do? We have produced a plug-and-play single photon source of Rayleigh single photons. We had noon state generation on chip. We have the generation of polarization entanglement, which is kind of, I call the queer type source for those of you who are interested in that. So we have generated entangled photon pairs on chip with the same frequency in 2 spatial modes. With cascaded nonlinearities, we also have generated on-chip free photon states. We have been building optical squeezing using waveguide resonators, narrowband photon pair sources by adding waveguides or combining waveguides with specifically designed mirrors. Lately, we also put waveguide resonators together with integrated modulators to tune them with electro-optic tuning. And we are looking at quantum interferometers for applications, something like SU1 in quantum interferometry. Now, one of the most advanced systems we have been implemented was a Hongo-Mandel interference on chip, and this I want to present you a little bit more into detail. I think many of you know what Hongo-Mandel interference is. It's if 2 photons are impinging on a 50-50 beam splitter, we have quantum interference. Here you see the 4 classical possibilities for 2 particles who are kind of redistributed via this beam splitter. Because of destructive quantum interference, the possibility that 2 photons leave at the same beam splitters cancels out. And this is the famous Hongo-Mandel experiment. It is the basis of measurement-induced nonlinearities. It's a fundamental quantum property. It's at the heart of linear optical quantum computing or any quantum networking. The experiment of Hongo-Mandel, typically in free space, is done such that you have a photon pair here in the modes A and B impinging on the 50-50 beam splitter and to introduce a variable delay and look for coincidence detection. The trace you expect is if you have a large delay that you have not the effect that both photons leave at the same output port, so the coincidence occur, while if you have 0 delays, no coincidence detection is done. Now, one of the tasks we wanted to do as a benchmark device, how do you do these things on chip? And here you see our experiments of a monolithic integration of parametric down conversion source and a 2-photon interferometer and a delay line on chip. Let me go briefly through the system. So we have a PDC source of type 2, so our photon pairs are generated in 2 different polarizations. Then we have electro-optic control, which allows us to change the polarization of these devices. And actually, via the bioreference modeling, we are able to implement a fast optical delay. And here we have a 50-50 beam splitter, and this 50-50 beam splitter then serves as the Hongo-Mandel interference beam splitter. In detail, so we start a photon pair H and B being generated. We separate them by the integrated polarizing beam splitter. Here you see the segmented never polarization converter. And now because the photons travel with different polarizations at different speed, if you switch the first segment, you see here the 50-50 beam splitter as you just saw, the Hongo-Mandel interference. Now, if you switch at different positions here in our segmented polarizing beam splitter, you see that the 2 photons in the upper and the lower paths travel at different speed, and we effectively introduce a delay. And this delay should then allow us to see the home dip. This is theory in experiment. Depending on which segment we are switching, we should see the red trace such that we get the bunching. If we wouldn't have the first switch in the beginning, which I haven't explained, then there would be always a delay, and you see the blue curve there. And this is the reason how we, this is the way how we implemented that, and this is how we expected it from theory. Experimental data looks very much the same, and now we can kind of retrace which kind of delays you've introduced with that switching. And what you can see is that we have implemented a nice Hongo-Mandel dip with a high visibility of over 93%, and the time delays we can introduce in that way are around 12 picoseconds. This is interesting. For us, it was a benchmark device, but not only as a benchmark device, you can also imagine that an element like that you can have in a quantum communication network, and this can help you, for example, for source synchronization. With that, I would like to switch gears. And I told you we are not doing only integrated optics. I'm going completely to the other side. Now I'm talking about the networks. Here is another picture of our lab, of our time multiplex systems. And in these systems, we try to get scaling not by different spatial channels, but by different time bin channels. We're interested in quantum simulation experiments, And kind of one of the paradigm of the most classical ways of looking in such large-scale system is by comparing random to classical walks. Now, a classical random walk, you probably have heard from your studies, is one of the most basic elements if you want to study propagations. Or it's the following: we have this small little guy, he walks on a line, but he doesn't know which direction he wants to go. So he throws a coin, and depending on head or tail, he takes a step to the left or right. And you see here this famous golden board. If you repeat that for several steps, here shown on the time, what you end up is at the end, if you look at the distribution, where the walker will end up in dependence on the different positions, you get the famous binomial probability distribution. It corresponds from a physical perspective to a diffusive propagation and is characterized by the fact that the variance of this distribution scales with the number of steps. Now, we can make this random walk quantum by introducing a quantum coin, and then the walker goes simultaneously, depending on the coin. Again, this is a two-dimensional Hilbert space, a step to the left and to the right. And then we kind of effectively look at the same distribution, but instead of having at every position a decision point, we put 50-50 beam splitter, and we get an interference pattern. Well, the coin is a quantum state. We are dealing here with superposition states, and the distribution at the output of such a device looks completely different. It corresponds to a ballistic distribution and is characterized by a variance of scale with the square root of step size. And here you see quite distinct difference between classical and quantum. A classical random walk has this binomial distribution, while a quantum walk with these superpositions has this widespread functions. And this is how quantum walks have been reduced. Now, one might ask, what makes this quantum system quantum? Well, in the classical world, we have particles who travel at several paths, while in the quantum world, we have here these superposition states. So the wave-particle dualism for single photons traveling through the systems makes this quantum. I hope you remember that later on. This is only partially of the story. Why is that interesting? Well, it's because random walks have applications for simulating in quantum computation in different ways. Classical processes like the Brownian motion, biological systems like deer wandering, and actually also the Google search algorithms, I was told, is also based on a random walk algorithms. Now, the idea is, or this is people are for sure, that quantum walks can be used in the same framework. We can model semiconductor physics systems with such quantum walks. Quantum biology is a topic which comes up on different occasions. And of course, this is also where quantum walks were introduced. It's one way of developing new quantum algorithms. Now, how do you implement such a system? Because we want many, many steps, that means many modes. And the way we came up with was a time multiplex quantum walk. Here very briefly, this is experimental setup we're using. We have here a switch which can, when our input states are switched in the system. Then we have electro-optical modulators or half-wave bits. So the encoding for the coin is polarization with H and B as two different coin states or coin possibilities if you want. And then here you see that we introduced by a loop geometry a polarization dependent delay. I will explain in a minute how this works. And then we feed back our system and we either detect our photons or we bring it back into the loop. Why is it a quantum walk system? Well, let me go to the beginning. We couple in, we meet the half-wave plate. This is the coin operation, the polarization degree of freedom. Now we have two polarizing beam splitter and a different delay between those two. And here you see what's happening depending on the polarization. We either introduce a delay or we don't introduce a delay. This is our step. So the position is done in time, and the step operation corresponds to relative shift in time in the position space. Now we are behind our loop geometry. We feed back the same signal. And you see here, we come back to exactly the same system. We take the two pulses into the system again, and you see that we have the case where the pulses traveled once, the upper one, the step one, the upper, and the step 2 the lower one, and then we get these interferences. And a nice thing, because it's a loop geometry, we can repeat that over and over again and get our quantum walk. Moreover, I told you that we can use half-wave plates or EOMs. If you use electro-optical modulation in the system, it's quick enough that only individual pulses are switched. So we have full control over our quantum walk systems, and we can simulate all kinds of things. This is one of our earliest experiments. Here we implemented a quantum walk over 28 steps. And here you can see that this works perfectly. So the red bars would be classical, and you see theory against experiment. And we have a very good quality of the data there. It corresponds to quantum walk if you want to do it in the spatial domain of the 406 beam splits and 29 detectors. Here you see also the good scalability. And we see extremely good preservation of the coherence. This is because we have a very resource efficient system, and the ideal homogeneity comes from the fact that we're using always the same elements. Now again, we have been doing that for more than 10 years. We demonstrate these time multiplex quantum walks. We studied decoherence and disorder phenomena. We could also translate that to two-dimensional quantum walks. We studied decoherence and losses, calculated graphs, graph engineering, state transfer. Then we went to more applied things. We looked how we can study systems with topological invariance, how we can simulate them. We looked for quantum walks before D coins and also for measurement-induced dynamics. So we saw that this is a very nice system to study these coherence properties. However, some of you might have asked, in particular if you're coming from classical optics, what makes this system quantum? Because effectively, if one is honest, all of these experiments were done with coherent light at the single photon level. And then the natural question, what makes the system quantum? And if you want to go from classical optics here to some real quantum optics, we need many particles, effectively home dips. And we have another boundaries that we do not only look at these coherence properties, which also classical light has, but at multi-particle effects, where we really enter the framework of quantum optics. And this is what we achieved in the last years too. So now we started to do this quantum walks not only with individual input pulses, but with two single photons as an input. And here you see that we had to implement a specific source for that. It's a parametric down conversion source, which gives us very nice photons. We have a network which we can fully control, and we showed that the coherence properties are nice, and then we have detection. And then we wanted to demonstrate an experiment where we really can study how the relationship between coherence and quantum effects, meaning quantum interference, is done. For that, we devised a very specific network, a specific experiment. So we put in two single photons. These were heralded single photon states you see in that acceleration area. Then we programmed our network such that we could program two different scenarios. In both cases, the blue one and the red one, so the single photons, were put into superposition states of photons impinging simultaneous on the blue, and the two beam splits from the blue side on the red side. But we programmed it such that the coherence properties between these individual photons, which are now delocalized over these networks, are different. They were different in such a case that in the one, we had complete superposition, which were completely equal between red and blue photons impinging on these two beam splits. In the second one, we introduced a phase change. So we changed kind of the coherence property, the first order coherence properties of these single photons. And for these two different cases, you see them again here. Here, the two red pins impinging here on the photo, the two blue pins and the two red pins. We looked now for different detection schemes. If you look individually, and we call it in a time-resolved manner to our system, and we ignore that there's a second system there, so we recorded the counts and looked for coincidences from the left side and the right side individually. You see for both of the cases that we get nice home dips. This is not unexpected, because at the end, you just neglect that there's another thing. If two single photons have been impinging on that system, well, then this is what I expect. The second thing, we did look for global interference properties, and we kind of didn't care on which side of this beam splitter the photons imping. We only cared, was it red or blue? And again, we looked for a global two-photon interference property. And what you find is that in the first case, that we again get the light home dip. This is because we have the equivalent coherence properties. While in the second case, this global interference property completely vanished. And so you can see that by controlling the coherence properties of these individual photons, which are delocalized over these different sites, we could control their global interference property, and such control of quantum interferences might become really important for quantum networking later on. Now let me switch to the last topic, temporal modes of pulsed light. I don't know, maybe how much time do I have for that? Okay, I keep going, please stop me. So we have seen two ways of kind of scaling up system, and now I want to show you the third one we're pursuing, and I'm talking about temporal modes of pulsed light. Let me first start talking about temporal mode encodings in channel. So you could have time bin encodings where we kind of have different timestamps corresponds to different quantities, different bins, different qubits, and the information is encoding in time. You can do the same with frequency, where if every individual frequency corresponds to a specific property. And you see that we are living in this time frequency domain. Now what we're doing here is now kind of an encoding which is neither time bin nor frequency bin encoding, but so-called pulse temporal mode encoding, where we encode simultaneously in this time frequency space. Why is that interesting? It's a different way of encoding information, of choosing a different high dimensional alphabet. And if that might look strange for you, in spatial modes, you're used to that, to have something very similar to these pulse temporal modes. This high dimensional alphabet has the advantage, if you do such an encoding, that it's fully compatible with waveguide devices and fiber networks, and that we can really process it nicely. Now, the problem is, if you're talking about these pulse temporal modes, how do you actually measure these pulse temporal modes, and how do you manipulate them? And this is where we started to look into that and where we got interested in these systems. Now, let me start again from a kind of introduction to that topic. If you're talking about frequency modes or quantum optics, you use that effectively you're talking about monochromatic creation operators. Basically, we say we want to have a quantized field, and before you even quantize your field, you say have a monochromatic frequency and a quantized band. Now, these monochromatic operators can't be the full truth, because if you have something which is monochromatic, you do a Fourier transform, and you immediately will see that you have something which is infinite in time. Now, if you want to have a realistic scenario, you can't have something which is infinite in time, but you have to introduce something which has a spread in frequency, basically a wave packet, as we are using it for ultra-fast pulsed laser system, for example. And this wave packet is a coherent superpositions of different frequencies, and we've introduced an envelope function. If you do a Fourier transform, we have also in time now a nice system which is localized in time, and you see that now we are talking about realistic functions or realistic objects. The interesting thing, if you have accepted that you can introduce envelope functions, here I had the first example, a Gaussian envelope function. We can now start to introduce different envelope functions. And here you see I use the Mead modes. And with that, we now define the field orthogonal temporal modes, these pulse modes I was talking about. These are orthogonal in the sense that if you integrate over them, that we get 0. And effectively, you can think about these pulse temporal modes equivalently in terms of information encoding to different monochromatic modes. So then typically you can encode your information, and these are just constituting a high dimensional system as you would be used for other systems. The only difference is that they overlap in frequency and time, and you have to have better sorting elements. Now, over the years, we have learned to control these temporal modes by spectral engineering, and you need them because effectively, if you want to have a state preparation and you want to use these parametric down conversion sources for having a good two-photon source, what you want is that a pulsed pump light generates a pulsed signal idler photon pair, but for that, you need already to control these temporal modes that only these Gaussian modes are present. And the way we kind of typically look into that is that we look at joint spectral amplitudes, and we have very specific dispersion properties, group velocity matching, such that we have here, for example, a circular system in these joint spectral intensity measurements. Now, by shaping the pump pulse, we can play with these joint spectral intensities or amplitudes, and we can play with a higher dimensional system. We can control these temporal modes, and this is what we're doing these days. Now, I told you that I also need a device for manipulating such systems. And the way that we can manipulate them is we use another nonlinear process. So for manipulating and detecting these things, we now do not use parametric down conversion, but sum frequency generation. The sum frequency generation has, again, very specific dispersion properties, such that we have transfer functions here. Instead of the joint spectral amplitude function, this is an input frequency, and we transfer that to output frequencies. And if you have the right properties of your crystals you're employing, you can manage that the transfer function is aligned along one line, so to speak. All frequencies which come into the systems are converted to the same output. If I say all frequencies, only the frequencies at the end which have a specific shape can be used then. So the pump which we basically put into this device defines which of the modes here we're impinging in that system, where we have different modes present, different pulse temporal modes. And then we're converting only one of them, in the first case, the Gaussian mode, to different frequencies which we can detect. Changing our pump mode then addresses different of our input frequencies, and this sum frequency generation allows us now to have this additional possibility to play with these temporal modes and to manipulate and detect them. Now, a little bit more into detail. So this is a parametric down conversion source. We pump it with a pulsed pump light, and the signal idler generated. I told you already that energy and momentum conservation has to be preserved. Now, I also told you already that this results in a joint spectrum. Now I want to explain you a little bit more into detail how that works. Now, this joint spectrum contour plots, so the energy conservation, now this is the frequency of signal and the idler, and you see the energy conservation just gives you a curve which is aligned at -45 degrees if we have different frequencies available or possible where we can have all of these different frequencies possible. Now, the phase matching condition, if we're in a waveguide, they are traveling in the same direction, but nevertheless, they're traveling at different speed. And because they're traveling at different speed, we get a second contour plot in the frequencies domain. So this is signal and idler, where the angle of these, or the properties of these phase matching properties are defined by the dispersion of the waveguide. Altogether, every process is defined by energy and phase matching, and we get these joint spectral amplitudes where this is signal frequency and idler frequencies, and you see you get in general correlated function. This is the maths behind the things. We have these correlated functions, and signal and idler frequencies are prepared. Now, what does that correlation function mean? Well, this is basically what you see immediately is that this function is not a function which factorizes. So in general, we don't have just one photons, but we have to take this internal structure into account. And this people have done by doing Schmidt decompositions. Now, a Schmidt decomposition is a mathematical tool. We use this function, joint spectral amplitude function, and we decompose it. And we decompose it in the following way. We define temporal modes as I introduced them beforehand. And these temporal modes now are defining these pairs. So effectively, what this process does is if we have a correlated joint spectral amplitude, our process produces pairs of pulsed temporal modes. And the effective number of modes corresponds to the amount of entanglement. And here you see in a pictorial way what kind of state is generated. So we have a pair of photons where signal is in a Gaussian temporal mode and idle in the corresponding one, or the first and mid mode, and so on. So in general, if you have a waveguide and you just pump it with a pulse laser light, you will have all these different modes already present. Now, if you want to have only one pair present, then you have to get rid of them. And you have to modify your joint spectral amplitude in such a way that you have no correlations in the system. And this is nowadays called source engineering. Then you have only one wave packet present, or only these temporal mode present, one of them. And this source engineering is an ideal PTC source for integrated networks with multiple spatial channels. Because you have pulsed light, you can synchronize that, you can have high purity single photon states by heralding, you can have very high brightness of source, and you have pure squeezed light sources if you want to go to the continuous variable regime. Now what we are doing is we start from these engineered sources, and now we play around with different envelope functions for the pump pulse. And interestingly, this allows us to have a complete control about the temporal modes. So it's not that we just have one temporal mode set, but we can really fully control which temporal modes and what the dimension of these temporal modes are generated. And we combine this now with the detection of the temporal modes, where we use the quantum pulse gate. And the quantum pulse gate is the device which I explained for the intro already. We have a dispersion engineered sum frequency generator with a very specific dispersion engineered sum frequency generation, such that the sum frequency generation is also a single mode process, and it only selects the modes we are aiming for. Now, a few more details about the pulse gate. This is coming back to our technology. It's a home-built apparently port lithium niobate waveguide, which has a small polling period of 4.5 micrometers. And the nice thing is that our input states are around 1550 nanometers. So in the telecom regime, our pump pulses, which we use for conversion, is in the TISAP regime. And this device has the specific properties that we can really address individual modes. We can select arbitrary temporal modes in time frequencies and also at time-bin superposition modes. We reconstructed the PWM elements of 7-dimensional mutual unbiased basis states. And here you see now we are coming to the area of quantum communication. So these 7-dimensional states with all kind of mutually unbiased states can be used for information encoding now, and this is what we are working on. One experiment we also did is we combined the PTC state with this engineered PTC state. We can control the modes with the quantum pulse gate. And here you see an example where we had only one mode present, and we analyzed here the joint spectral intensity, and then with the quantum pulse gate also the modal properties. And you see that here in this graph only that one Hamid mode was present. Then we changed that to a Hamid Gaussian mode, and then we kind of could implement in that an entangled state in these mode bases. We could prove that again with that quantum pulse gate setup. Now, maybe, is there any time left? Anybody still hearing me?
Yes, of course.
Okay.
15 minutes past.
So everyone hearing you.
Okay. Do we have 5 more minutes, or should I stop here?
I think 5 minutes is fine, I guess.
Okay.
So Deepa?
Yeah, sure.
Yeah.
I just want to give you a glimpse where these quantum pulse gate, where we can operate on these modes, can be also used. And this is quite interesting because there is a way for parameter estimation of incoherent emitters. This is a new topic which came up and which we find quite interesting. It was introduced again in the spatial domain. The question there was, you have two stars which you want to estimate the distance between those two things. There's incoherent light coming from the stars and you want to estimate the distance. How well can you do that? And of course, what you can do in space, you can do also in the frequency domain or in the time domain, and you can ask if I have two incoherent emitters and there's a distance between them, how well can I do that? Now, how well can I do that? You can do in a classical treatment or in a quantum treatment, and here you see just the theory which is behind. You can use estimation theory to treat this problem, and you find, and this is kind of the trick, that in the quantum domain, if you use a quantum information approach, so it's called quantum Fisher information, you do better than you could do in a classical framework. In which sense do I mean that? Well, here you see the two different emitters which kind of send light out, and you want to get the distance. And you see that the statistics very quickly doesn't allow you to distinguish between these two systems. And you know that very well, all of you. This is nothing else but the Rayleigh limit, right? If you have two emitters which have a broad distribution, you bring them too close together, then you can't estimate this difference anymore. Interestingly enough, if you do a quantum information treatment of that, you find that if you do the right measurement, a mode selective measurement, that this curse is not true anymore and can always estimate how far they are away if you do the correct measurement. What you need for that is really the coherent detection, and this is what we did in the time frequency domain in our lab. So we generated two different states and we estimated the difference between them. And we did not only estimate it for two beams which have individually the same height, but also with different heights. Here's the experimental setup. If you're interested, I can explain you more in detail how it works. But the idea, what we really wanted to have, we wanted to estimate the different distance between that here in the frequency domain, where we had the constant width, but we brought them closer and closer together. And what you find is that you can always estimate that separation. Even here you see that in this graph, if I just looking at detections or intensity measurement, you say it would be not possible to see that at all. You see that this works very nicely. The tool we used for that was exactly this quantum pulse kit, where we can measure on these coherent superpositions. Now, I told you that we are also doing it for different intensities, and you can go further. You can ask not only what is the distance between, what is the centroid, and what is the height between those two things. Quantum mechanically, this is not trivial because these properties from a measurement point of view are non-commutative. So we have something like a Heisenberg uncertainty principle. But if you are able to shape the selection of your coherences, you can do these measurements, and effectively we were quite proud of that. Last year we could show that we can do such a multi-parameter estimation, and this quantum pulse kit can help you to really get enhanced performances. Here you see for all kinds of different parameters, here the distance between them, the centroids, and the different heights. You can do better than classical systems could do. And the measurements are the quantum Karma-Rao simultaneously. This is basically the limit, which is analogy to Heisenberg. Okay, this was a long talk. Thanks for listening. It was an overview of all kinds of things we're doing. To sum up, I showed you first of all nonlinear integrated optics quantum devices, and I think this is the basis for practical quantum technologies, and we are trying to develop that. On top of that, there's other ways of scaling up systems, and I think we will need them. I talked about time multiplex quantum systems and our idea and approaches to see what is quantum and classical. And last but not least, I talked about temporal modes, which brings you to the field of pulsed light and how you can play with different ways of manipulating this pulsed light of the intrinsic mode structure to really also accomplish high-dimensional systems, for example, for quantum communications. What's next? Well, the technology, and we see that already now, goes from, these large waveguide systems to lithium niobate, LNOI, lithium niobate on insulator. We're also interested in that. This will give the whole field another push and makes these lithium niobate systems even more important. You have to scale systems, and time multiplexing is a nice way. So we have an experiment where we have GHz state generation with a boost of time multiplexing. We need the benchmark in the quantum characterization. So we also do work on really characterizing large networks. And last but not least, I didn't have time. We're looking for different applications of these pulsed light, for example, quantum spectroscopy with time frequency entangled light, and quantum communication with quantum pulse gate devices too. So I'm at the end. Let me thank you again for your attention. I would also like to emphasize that this is not my work in principle. There's a lot of people involved and I'm proud of my group. All of them are doing great work. I would like to acknowledge the founding agencies, and well, we're always looking for people. So thank you for your attention.
So much. I see that Anil is here, joined. Anil, would you like to take over?
Perhaps he's not there, I think.
Oh, shall we move directly to the Q&A?
Yes, I think probably that is, yeah.
So that was a wonderful talk, giving a great overview of different technology possibilities with quantum devices, integrated optic devices. There are several questions. Let's try to get to them. Before that, let me take this opportunity to ask you my question first. I mean, I'm completely from a classical communication background, and this pulse temporal modes that you were talking about sounded very similar to orthogonal frequency division multiplexing, where we give different pulse shapes to different frequencies. And I mean, so of course, these are all done at single photon levels, but is that the right parallel?
I think it is, to be honest. This is something, thanks for that wonderful question. This is something where I have to say that quantum optics people discover things which classical optics people also know. I guess we are running these systems, and you have to tell me if that's correct, at different time scales, because this is femtosecond pulses, and as far as I'm aware, in classical systems you don't do that, and I don't know how you do the sorting there, but I think this is the different thing. But at the end of the day, you're absolutely correct. These things could be combined, and of course you could use it for dense classical encoding too. I think this is where it's nice, and you can use them for squeezed light equivalently to all of the other things. The thing which excites us is the device, this quantum pulse gate.
Okay. I'll probably take it up later with you for discussion of that. Ashutosh has a question. In the experimental results of quantum walk, there are some minor deviations from the theory. What could be the source of deviation? I mean, is that just the statistics in the experiment, or?
Yeah, I think this is a minor imperfections. Like these walks are extremely sensitive to any deviation of half-wave plate rotations or minimal losses. So it's an exponential scaling, and we are at power to the 28th. So if you look at quantum walks in the spatial domain, we did that, I should say, with our couple. They look much worse, but you still see minor deviations because as I said, you're extremely sensitive to anything, which is not ideal.
Sudarshan has a question. How to make 90 mm pattern on a lithium niobate chip? Lithography field sizes are much smaller.
Sorry,
how do you make a 90 mm pattern on a lithium niobate chip? I probably, was there something in your slides which said that?
So maybe I can clarify a bit. I think you have shown your lithium niobate that pipeline waveguide structure is of length 90 millimeter. So how you do patterning of 90 millimeter long 90 millimeter long waveguide structure, 9 centimeter, yeah.
9 centimeters.
This is just depends. It's a standard lithography, and this patterning is still, depends on your machines, but this is still feasible.
Yeah, this is, I think, Sudarshan, this is just, I know that because I worked in that lab. So it is a contact lithography. It is not like a stepper. You don't need to bother about field. Whatever things are there, that is in the mask actually. But once you get the mask, it is just a simple contact lithography process.
Yeah, it's this is why I said it's a standard mass contact lithography. We are not at the level where we have nano systems already. We saw that it's a micrometer, and this is from the size. This is pretty normal, I think. This is what you find in mass production too. It's the more tricky thing is how do you get this periodic polling down to 4.5 micrometer, and this is not limited by the lithography, I should say, but by the way how you can control your periodic polling. And there we did over the last 10 years quite some work. But our smallest pollings we have is 1.7 micrometer and below, and this is really quite something. But it's an optimization of the way how you process the polling. But the lithography is nothing special if you want.
The next question is regarding the sources. What is the maximum value of the purity of the source achieved so far?
What is the which value? Sorry, it's just the
purity of the source.
The purity of the source. Well, we have been optimizing the purities really a lot, but we don't have apodization. So our purity corresponds to a G2 value of 1.9 somehow, and it depends how you filter that. So it's something around 90% these days. But having said that, with apodization, so if you have periodic polling, which you also structure at the edges, you can achieve even better purities. And in the literature nowadays, people have achieved really extremely high purities, also for integrated systems.
The next question is something related to what you probably touched upon at the end, lithium niobate on insulator. What is the prospect of that in this research? I mean, some material.
I have to say this, what I presented you the concepts there, and just recently, if you look, there's a very fascinating work by Longcast Group together, I think, with Feya and also Franco Wong, where they show extremely good quality on these sources. And personally, I think that this will be the future because, well, you can minoritize things. Now, having said that, for many other applications, like for example, for communication, one of the challenges is to have extremely high efficiencies and also interfacing. And to be honest, there's probably a long time where also these conventional devices will have their place. But if you think about computation, I think it's a very promising platform.
So, Deepa, I can have a related question here to Christine. Christine, you know, LNY at this Longcast Group, you were just referring, that is really promising. I'm also thinking of switching back to lithium niobate. Always Professor Tyagarajan also asked me to, why don't you go for lithium niobate again? So one problem I see that, you see, normally whenever you are going for PDC, parametric down conversion, so your wavelength is just from 750 to coming down to 1550 nanometer. That's a wide wavelength range. And in LNOI, this good part is that you can have a very tightly confined guided mode. But that will lead to a very high dispersion. Yeah, so that means you have to have your dispersion compensation, broad band dispersion compensation needed for your conversion, right? So how that can be managed? Is there any way out?
I think that the dispersion compensation, you have to design your system correctly. You're right that the dispersion then is not governed only by the material dispersion anymore, but by the modal dispersion. But you need to control that. Actually, a lot of the ideas I showed you in the last slides, I didn't go into detail about these pulse systems, use a dispersion control. So yes, you have to control your system very precisely. You have to design them in advance. So you have to make clear that the geometric structures you're using are the correct ones. But actually, this is even an advantage of LNOI. So you can't just produce waveguides and see what they do. You have to model and simulate them beforehand. And I can tell you, because we are looking to these things, it's Longcast, and they're doing a good job in that. They know exactly what they do. But this is not an issue. Not at the end. You have to care for it, but then it's not an issue. Is that answer enough?
Yeah, okay. Yeah.
Okay. So the next question is probably a little more general. It's about the term single photon source. We attach with signal idler generating sources based on spontaneous Fourier mixing, parametric down conversion, etc. In these modes, the photon count in a single pulse is probabilistic, and we cannot assure that there's only one photon in a given pulse. Hence, isn't it misleading to title these sources as single photon sources?
Yeah, absolutely right. Thanks for pointing that out. I started off with Gaussian boson sampling, and there you see already one way out. If you look at the full statistics of these sources, actually a photon pair source is exactly the same like a two-mode squeezed source. So one way is you look at continuous variable systems, but maybe that's not what you want. But you have to drive them at low efficiency, such if you really want to use them at single photon sources. And the way out there is what people have also already demonstrated is multiplexing. So you have to produce several of them and you stack them together and select things. I think honestly, of course, there's other ways, but the more the systems become integrated and the more technological advance they get, this multiplexing becomes more and more realistic.
In the quantum walk experiments, what's the scope for studying 3D quantum networks using synthetic dimensions such as polarization or frequency control, since your systems already have polarization control capabilities?
There's a question how we can make it 2D, a 2D system effectively.
3D.
No, 3D. 3D.
So 2D,
Can you add polarization, for instance? You have time frequency. So
I hope that wasn't confusing. In the quantum walks, we use the polarization already. The polarization is the coin space, and we're using temporal bins. Now, if you want to make it more dimensional, what you can introduce is different time scales, and we did that for implementing a 2D system already. Now, if you use 3 different time scales, you can go n-dimensional. And the question is, how do we get that coin space up? Because if you want to cover the whole thing, now we also have demonstrated 4-dimensional coins, and this is a clever design how you combine different timings with different polarizations together. So we demonstrated a 2D system with a real 4D coin, I would say. We demonstrated a 1D system for 4-dimensional coin, but this time multiplexing can be used in a clever way to also try to synthesize higher dimensions. Now, how efficient that is at the end is always the question, because the more time scales you introduce, the longer you have to wait. But again, also these ideas people have been looking into that, and you can play around here in implementing different dimensionalities in coin as well as in time space. And of course, in principle, you can also use frequency dimensions if you want. And this is also the overall idea. This is why I present you these different ways: the spatial encoding with the integrated optics, the temporal encoding with the time, and frequency encoding. And then you can play all kinds of different games if you want. At the end, you will have to find efficient ways of scaling our systems as a photonic as a whole.
The next question is, how efficient is the generation of pulsed temporal modes with frequency sum generation as compared to narrowband compute? How efficiently can you generate the pulsed temporal modes?
Again, here we have an engineered system. So the efficiency is not less, but actually at least equal. I think it's actually more efficient. Well, if you're only going with monochromatic modes, you can have and probably equally efficient, but these quantum pulse gates are very efficient. This is because we make sure that the group velocities of the pump and the input is the same. And then you have a very efficient system. So we demonstrate efficiencies for the pulse gates up to 50%. And then other things kick in, like time ordering issues, so then quantum mechanics also plays a role. But then you can have cascaded pulse gates. In principle, 100% is feasible. And there has been a work by Mike Raymer where he has cascaded 2 of them, showing that in principle, also 100% efficiencies can be done. So there's twofold. It is more efficient than, at least as efficient with monochromatic light. This pulse light is good. And maybe the second answer, 100% efficiency is feasible, which is important if you want to use these things as add-drop filters.
Wouldn't dispersion be a problem? The shorter the pulse shorter
Yes.
you make.
You must make sure that your phase matching is flat. That means that within the length of your crystal, that the pulses really don't have third order dispersion effects which they experience. So these kind of things come into game, but this is a question of engineering at the end.
The next question I will slightly rephrase and ask, is there a concept of periodic polling that exists in LNOI?
Sorry, is there
periodic polling, PPLN, periodic polling can be implemented. Can that be a concept that can be implemented in LNOI?
Yes, there's several work which people have demonstrated that, I don't know how many, but if you look in the literature, this is absolutely feasible.
Okay. So those are the questions in the chat. Any other questions from analysts or anybody else?
Yeah, I had a question. How about using different spatial modes of waveguides instead of using signal mode waveguides for increasing the dimensionality of the quantum system?
Yes, it's also a question of control. Yes, you can do it. I know that with optical fibers, people have been doing that. But then these waveguides, we have rectangular shapes and controlling. Yes, I think there is, of course, in lithium niobate, people have been using different spatial modes, and this is definitely also a possibility. Why not? The question is, we are not doing it, I guess, but there has been work also doing that you use different spatial modes, and then you have to control all the conversion into these different spatial modes. It's a question of engineering.
Another question, when you have this Gaussian pulse modes, a Gaussian pump would down convert to a Gaussian signal and a second order Hermite-Gauss idler. That has a non-zero parity. That parity is conserved still. So is that allowed at all, or is that disallowed in your process?
Are we talking about spatial or spectral modes here?
So the time pulse, the pulse mode.
I think it is allowed. It is allowed. You see it in the Schmidt decomposition, and one reason why you immediately see that it's allowed is we're playing with different wavelengths. So I think this parity conservation.
Because you had sort of pairs of Gaussian and Hermite-Gauss first order, Hermite-Gauss second order. I'm just asking. There is also a possibility that a Gaussian splits into a Gaussian signal and a second order Hermite-Gauss idler. There's no problem.
Yes, but these temporal modes are defined. No, there's no problem. But maybe you're right. The parity is conserved anyhow because there's free fields involved. There's
Exactly.
There's the pump, and then there's signal and idler, and they then there's the preservation, but we have free fields.
Correct. Yeah, but you don't see that at all in your experiments. This kind of output coming out.
This is a little bit tricky, Amalai. We do see all these different modes, but the process which is defining that is the correlation between signal and idler. So this conversion we control, and we see that if we have the first Hermite mode as a pump, then we see exactly what you say. Then we are generating a signal Gaussian with an idler first Hermite mode, and vice versa. This is how this entanglement generation is done.
Yeah. Okay. Yeah. All right. One last question. What gives a better resolution in quantum imaging of two incoherent sources that beats the Rayleigh limit? What is the physics behind improved resolution?
The physics behind is exactly in the spatial domain. If you have, how should I say, if you have a goal, if you can measure on a coherent pulse, and you ask what is kind of from a coherent pulse the first derivative, meaning a displacement, then you find it's the first Hermite Gauss mode. Now, if you're measuring on the Gaussian mode and the Hermite mode in a coherent fashion, then you can measure these separation very precisely. That's exactly what's also the physics which is behind that. It's basically playing around with measuring these derivatives and otherwise exactly the symmetry properties. And if there's any small displacement and you see that nicely, then you see that the symmetry properties are broken, and this is how you measure it.
Okay. Thank you. I'm done, Deepak. Yeah.
Yes, I have a question regarding this. For full-scale integration, probably you may need the detector as well. So, can you please comment on that? So, what kind of detectors for single photon detection available on this lithium niobate? Is there any hybrid options are there or not?
Yes, there's SNSPDs, which you can implement on top of this lithium niobate. We are developing, a junior professor in Paderborn is also developing them, but not only here. There's in the literature you find them already also electron LNOI and lithium niobate on this. So basically what you do, you deposit superconducting films on top of your structures, and then you have to kind of also design the evanescent coupling. But SNSPDs are completely feasible.
I have to just add one question here then. Your lithium niobate, you are operating at a higher temperature, I guess, that right? So now you want to integrate SNSPD and then you have to put in refrigerator at just any temperature. So
yes, you're right. In order to restrict photorefractive index in this, you typically heat your waveguides to 200 degrees Celsius. Now, there's two facts that several of our experiments are done at room temperature or below. First of all, we drive them pulsed, which changes apparently the situation that you don't have to, and we drive them at extremely low temperatures. So PDC, extremely low power. So PDC, we launch next to no pulsed energy, and there photoreflection doesn't play that role. We also demonstrated already that we can have PDC. This is a new Optica paper in this cryostat, so it's absolutely feasible. It's not trivial, but it's doable.
Yeah. Okay. Okay. Deepa, you just.
Any other questions from anybody? If not, I'll get back to my original arguments that in the concept of, in this orthogonal frequency division multiplexing, you do also have the time frequency mapping, and you pick orthogonal functions. And of course, there we do everything in the classical FFT domain. And here you seem to be doing it in more of a physical modulation kind of a domain, right? But otherwise, the concept looks the same to me. And then again, we say that the resilience is like, you say using these pulse temporal modes, you're able to, for example, improve the stellar resolution. Here again, we say in the corresponding resolution is the frequency resolution here in the classical picture, and we say that the resilience to noise is much better, right? So I see an exact parallel there.
Okay, so I don't quite understand if I get the answer, the question, but let me try to ask you if that's the question. You say the signal, so you are referring to the signal to noise ratio, and you're kind of puzzled why that should be better with these
if you're doing this kind of time frequency mapping, and you basically encode your information on these kind of eigenfunctions, which are orthogonal functions, like what you showed, you do get a better resilience to the signal against resilience to signal to noise ratio. So I see something like that is happening here as well.
It is. It absolutely is. And there's work from Konrad Banaszek actually for looking at communication systems, actually classical communication systems, what you could gain if you use pulse gates for noise filtering.
Right.
And if you're interested, look out for that. He demonstrates that you can gain a lot because there's two things. Yes, it's a perfect noise filter because you kind of take these coherent things out.
Right.
And then for the single photon level, you also gain if you do not use homodyne detection but click detection. These on-off detectors can have advantages in terms of noise there too. And as that my colleague here demonstrated also for classical system, this kind of approach of selecting with a pulse gate or with these things on specific modes and doing at the single photon level detections actually has also advantages there. And yes, you're absolutely right. In terms of noise, these encoding also is very beneficial. This is what people are starting to look into. And then you combine immediately the advantage from this different detection scheme, which is also classical, and you can directly combine that with quantum communication. I think this is a very attractive thing. I told you that we're looking for applications for quantum pulse gate, all these things. And yes, it is an extremely useful tool for noise filtering. You're absolutely correct.
Thank you. Thank you for that. Questions? The questions, shall we close the session?
Yeah, I think we have, I think if any other questions, I think Arnav, you can note down, we can pass down to Professor Christine later. Maybe we have exceeded time. I think Christine might be missing her lunch probably. It is 1:30. So
No worries.
okay,
Yeah,
I
I
think
mean, thank you so much, Christine, for spending a lot of time patiently answering. Thanks to the wonderful audience asking wonderful questions. Thank you, Professor Tyagarajan, for,
You,
as usual, asking us the thought-provoking questions and making us
very
think.
interesting question. Yeah.
Wonderful talk, Professor Christine. So it was a wonderful talk listening to you again. Thank you.
Thank you very much for inviting me, give me the opportunity. See you.
Thank you.
Thank you.
Thank you.
Have a
Thank
wonderful day.
You too. Bye.
Yeah.
Bye.
Thank you, Bijoy. Thank you, Deepa.
Thank you. Thank you. It's a wonderful talk. Yeah. Thank you. Thank you.
Good
See you.
organization. Great. Thank you. See you then. Yeah.
Yeah.
Bye.
হলো আরে দীপ্তশ্রী ভোট অফ থ্যাঙ্কস তো হলোই না
হ্যাঁ কি জানি আর কিছু তো বললো না তো ঠিক আছে প্রফেসর দীপা বলে দিয়েছে তো দীপা